Hi everyone. Today we're going to talk about understanding t-tests. And before we jump in too far on t-tests, I want to go over a couple of distinct differences in the inferential statistic tests that we're going to be going over throughout the semester. And I realize that most of you probably don't know what most of these are, and that's okay. We're going to learn about all of these things. However, I wanted to go over this first so that you can understand there are some very subtle differences between each test, and some of that's in the language we use or in what we're expected to keep an eye out for. For instance, with the t-test up here on the left, what we're doing in a very rudimentary explanation is we're comparing the means or the averages from one group to the averages to another group. And it involves having two groups. We're comparing the means, and we're looking for a difference between the means. When we report a t-test, we're going to want to report a t-statistic, which is our inferential statistic, and our descriptives, and a Cohen's d, and the Cohen's d is the effect size. Now, let's look at ANOVA. An ANOVA is a lot like a t-test, but there's more than two groups. So we're again looking at the means, we're comparing the means, and we're looking for differences in means between the multiple groups. When we report an ANOVA, we're going to report our F statistic and a post hoc with the descriptives, and our eta squared, which is our effect size. A lot of this should be over your head. You probably haven't heard most of these words. That's fine. I'm just putting it out there so that you can kind of keep an open ear as we go forward for some of these things. So far, the t-tests and the ANOVAs are looking for differences in means. But when we consider a correlation is looking to see if there's a relationship between two variables, if there's a relationship or a correlation or an association, and whether or not a relationship exists. This happens when they're looking at linear relationships, and that can either be a positive or a negative. And again, we're going to go over this quite a bit more in the future. When we report our correlations, we want to report our R statistic and our descriptives and our R squared for our effect size. So at this point, you should realize a few things. Number one, we always report a different inferential statistic because we're running a different test. So a T statistic goes with the t-test, an R statistic goes with correlation, an F statistic goes with an ANOVA. But they all have the descriptives, and the descriptives are descriptive statistics that we've run on our variables that we are looking at. And we do this so that we have an understanding of the variable characteristics of the population that we're looking at. And they all have also an effect size, but they are different tests. So we run a Cohen's d with a t-test, we run an R squared with a correlation, and we run an eta squared with an ANOVA. Again, you're not going to understand all of this yet, but what I'm hoping to do, instead of confusing you, is to let you know that these things are going to be different. So each week when we're learning a new inferential statistic, I want you to be listening for and looking for the new terminologies that we're going to be using. Regression is a little bit like a correlation. It actually starts off as a correlation, and we go one step farther, and if we identify that there is a relationship between the two variables, we then look to see if the independent variable can in fact be a significant predictor of the dependent variable. So with a regression, again, we're going to report our R statistic to show that there's a linear relationship. We're going to report our beta statistic, our descriptives, and we're going to report the regression equation. We're going to get into all of this later. It's gonna be not as bad as this sounds. I know this was a lot to hear, but just bear with me. I just want to put a couple of these words out there so you can get used to hearing them. Now let's move on to our t-tests. And again, I think I've said again like 89 times already, and we're 2-3 minutes in. Sorry about that. Apparently that's going to be my word of the day. So just as a reminder, we're going to go we're talking about t-tests, we're going to be looking at comparing means. Let's get a little background. So the t-test is used to test the hypothesis about means or averages when the population variance is unknown, and that's usually the case. It is very closely related to the z, and it was developed when they were trying to test the quality of beer. There are three main types of t-tests. There's the single sample t-test, the dependent samples, or also known as the paired samples t-test, or the independent samples t-test. And you will hear throughout this lecture that I will go back and forth between the term dependent and or paired, because they are the same thing, and I try to use both of them to make you familiar with it. What we are curious, our main question, is whether or not the independent variable is affecting the dependent variable. So we can have this happen a few different ways. There can be we can have one independent variable with two levels. For example, gender. We have gender, and one level would be male and one level would be female. And we want to know if it affects the dependent variable. Or we could be looking to see if the independent variable might affect the variability of the dependent variable, where we might have the level 1 of the independent variable affecting the dependent variable's sigma for 1, which is the variability, or the level 2 affecting level 2, and looking at the differences between the level 1 and the level 2. We also might be looking to see if there's a difference in the average score of the dependent variable. So if the level 1, or the average of level 1, or level 2, and the averages, or the mean, the mu, of level 2. Most often in psychology, our hypothesis is going to work off of this last example, and we're assuming that there's a difference in the average scores and not the variability. The two most common t-tests are going to be your dependent and your independent. Now, the dependent, also known as the paired samples t-test, is a within subjects design. We're looking at the average of condition A, and we're seeing if there's a difference from the average of condition A to the average of condition B. So these are the same people when it's dependent. Dependent is looking to see if, think of a pre-test, post-test, if all of the same people took test 1, and then maybe they had a lecture, and then they took test 2, and we wanted to see if test A, if the average of test A was different than the average of test B. It's the same people in both conditions, in condition A and condition B. An independent samples t-test is also known as a between subjects design. We're looking to see if the average part of condition A we're looking to see if there's a difference from the average of condition A to the average of condition A, but two different people. So it would be maybe one class takes the test and then another class takes the test, and we want to know if there's a difference between the two classes, and there are different people. And this is the difference between the dependent and the independent. Both of them are looking to show us if the average score of a group is affected by the independent variable. What kind of t-tests? Single sample t-tests. A single sample t-test is when we have only one group, so we only have one mean, we have one group, and we're going to test that against a hypothetical mean. The dependent samples, and you will hear me discussing dependent and independent about 5 different ways, just because sometimes it clicks differently for different people. We all sort of absorb it a little bit differently. But the dependent or paired samples t-test is when we have two means, and we either have the same people in both groups, or sometimes we also have people that are related, like a husband and wife, or left-handed and right-handed, a hospital patient and visitor. So if it's something that's paired, twins would be often something like a paired samples t-test. Independent samples are when we have two means, two groups, and there's no relationship between the two groups. So a single samples test is when we have a single observation from each participant. The observation is independent from other participants, and we're comparing the mean score to the distribution of mean scores. A paired samples test. In a paired samples test, also known as the dependent samples test, which is the type of design is known as the within subjects design or repeated measures design, and you will hear these terms as well. And this is what we use oftentimes for a pre-test, post-test, or a before-after. We're looking to compare the mean difference scores to the distribution of means of different scores. And that's kind of a mouthful. And I have a chart in a few slides that will hopefully help break this down a little bit more. So we have a population of measures at time 1 and time 2. And we can take the average for time 1 and time 2. And then we have a population of, we create a list of the population of differences between the measures of time 1 and time 2. So at time 1, if we had 5 times of 6 o'clock, 7 o'clock, 8 o'clock, 9 o'clock, and 10 o'clock, and maybe our average time was 8 o'clock, then we would create the difference. So next to 5 o'clock we would have 3. Next to 6 o'clock we would have 2. Next to 7 o'clock we would have 1, because that's how different they are from our average of 8 o'clock. Those differences are what we're interested in. And again, we will go through this a little bit more in depth in a few slides. So what we're looking at is the population of the mean difference between measures at time 1 and time 2. Yeah, that's a lot. So another way to look at this is that we're going to compare the same dependent variable at 2 points in time. The independent variable is what happens between the first and the second measurement. The intervention, the experiment, the X factor, that's the independent variable. As an example, if we had a quiz score before and after completing a lesson, the independent variable is the lesson. Did you already have the lesson? Did you not have the lesson? Those are the conditions. And the dependent variable is your quiz score. Another example might be the level of confidence before and after a makeover. So you have your level of confidence before the makeover, you have the makeover, and then you have your level of confidence after the makeover. The independent variable is the makeover. Yes or no, have you had the makeover? Had the makeover, not had the makeover. The dependent variable is your confidence level. So was there a change or a difference between the confidence levels from before the makeover to after the makeover? And you'll notice that these are the same people. The people had the lesson, they had a before score, they had a lesson, they had an after score. They had a before confidence level, they had a makeover, they had an after confidence level. That's what makes it a dependent or a paired samples t-test. For the independent t-test, we're going to compare the differences between two means of two independent groups, also known as a between subjects design, and we're looking at the differences between means. The comparison distribution is a difference between means to a distribution of differences between means. So we have the population of measures for group 1 and group 2. We have the sample means for group 1 and group 2. And then we have the population of differences between the sample means of group 1 and group 2. Let's recap this. For a single sample test, we have single observation from each participant. The observation's independent from any of the other participants. And we're looking to test to see if the mean score of the distribution is different from the mean scores of a hypothetical. The paired sample test has 2 observations from each participant. The second observation is dependent on the first. So that's kind of a good hint as to why we call it a dependent samples t-test. We're comparing a mean of the different scores to a distribution of means of different scores. The independent samples, we have a single observation from each participant in 2 independent groups. The observation from the second group is independent from the first since they come from different subjects. We're going to be comparing the difference between 2 means to a distribution of differences between mean scores. Now, let's see what else how we can break this down and make this a little bit less confusing. We have a population. Our population is right here. A, B, 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 B. I don't know if I counted those correctly. A dependent or paired sample or a within subjects samples test would be if we were to take our entire population and get test 1 average, and we were going to compare that to our entire population of test 2 average. For our independent or between subjects sample t-test, we would be comparing the average of A to the average of B. So these are the same people compared to the same people, where these are this group of people compared to the B group of people. So, as I said, we would break this down a little bit more. What we're interested in for math test here, this column is for math test scores. So I have participants. Here's a female who took a math test, a history test, and a second math test. I have a female who took a math test, a history test, and a second math test. Our average for math test is 39. And we use often a statistical program to do this for us. But what they're actually going to do is they're going to say 33 from 39 is 6. 24 from 39 is 15, right? 36 from 39 is 3. They're then going to square it to come up with they will come up with differences from each row, and they will compare that sum, usually squared, to another group doing the same thing. So there is a little bit more math involved than we think. However, it's in general, the basic concept is we're looking at the differences in means between 2 groups. Now, if we had a group of students that took a math test and a history test, then watched a video on relaxation, and they were asked to take a second math test after the video, which t-test would we be running? So we're comparing math test 1 to math test 2. You want to ask yourself, are the observations independent from one another, or does one depend on the other? And you want to ask yourself, are the observations from different participants or from the same participants? So the independent variable for this would actually be watching the video on relaxation. And the dependent variable would be the math scores. And we're looking to see if there's a difference in means from this group to a difference in means from this group, depending upon after watching the video. Can you guys guess on this? This would actually be a paired samples or a dependent t-test. And the reason why it's that is because we're using the same participant is a part of both conditions. So they're part of the condition of the first math test and they're part of the condition of the second math test. Now, if we were interested to see if gender had an influence on history test scores, we would be comparing the female history test scores, and they would again be the mean differences, to the male scores. Are the observations independent from one another? Yes, they are. Are they from different participants or the same participants? They are from different participants. So this would actually be an independent samples t-test. Is it starting to sink in a little? Now, when we report the t-tests, we want to remember to report both the descriptive results and the inferential results. In APA format, the descriptives you want to have your number or your count, your mean, and your standard deviation. Our inferential, we need to have our statistic, our coefficient value, and our p-value, which would be, our coefficient value would be our t-statistic, and our p-value. You always want to state whether the results are significant or not. And you want to use that terminology. You don't want to say things like, there's quite a big difference. Significant in the world of statistics is where the line is drawn to determine whether or not something does have an effect or does not have an effect. So we want to use the terminology significant. You also want to be sure to address whether or not you will reject or fail to reject your null hypothesis. Inferential statistics are testing against the null hypothesis. The null hypothesis is going to say there is nothing happening, and when we're running inferential statistics, we're testing against that. If something is happening, if something is significant, then we would reject the null hypothesis that there's nothing happening. If something is not significant, then we would fail to reject the null hypothesis that nothing is happening. And it doesn't say it on the slide, but you also want to report your effect size. And just as a reminder, and hopefully this will sink in, but it seems like a few people are still having a few problems between a research question and a hypothesis. So a research question is the question that we're seeking to find the answer to. Our hypotheses are the possible outcomes or answers that might happen as we seek to answer that research question. So we have our research question that we develop. From our research question, we're going to get hypotheses. We're going to get one null hypothesis because there can only be one. And then there are a few different possible alternative or research hypotheses that we could possibly come up with, but we only pick one. So if we're interested in, well, actually I have an example. Let me go farther. What if we were interested in whether or not eye color, blue or brown, can influence the number of dates one has in a year? It's missing an S. Our null hypothesis is that eye color does not influence the number of dates, and it can be written in symbolic, such as X bar blue equals X bar brown. Our alternative hypothesis is that eye color does influence the number of dates, or we could be specific and give a hypothesis that blue eyes have more dates than brown eyes, or brown eyes have more dates than blue eyes. So you can see where you can't pick all three because these two are completely contradictory. But usually, based on our experience, we would pick one that made sense to us. Our hypothesis never has to be correct. We just put forth to the reader what it is we're thinking. And that's okay if we run our statistics and it comes out a little bit differently. We've still answered our question. And I don't know if you can tell, but this alternative one, it really doesn't have a direction. So this is called a non-directional hypothesis, whereas our alternative 2 and 3 both offer a direction as to where we anticipate seeing how we anticipate seeing the results play out. Let me show you what I mean by this. Our non-directional hypothesis is just that blue does not equal brown. That there is an effect, and we can write that as blue not equaling brown, that one will be higher than the other, but we're not predicting which one, or one's lower than the other. I break it down here where the hypothesis with the subset of A1 is the symbol for the possible alternative hypothesis. X bar blue represents the average number of dates in a year for the blue-eyed participants, and X bar brown represents the average number of dates in a year for the brown-eyed participants. And the equal sign with the slash through it means that it is not equal to, or does not equal. The directional hypothesis, which would be alternatives 2 and 3, here we have our hypothesis alternative 2 and our hypothesis alternative 3, and those are the symbols for just which ones you might pick. The X bar blue, as stated over here, it's the same meaning. It represents the average number of dates of the year for the blue-eyed participants, and the X bar brown, that shouldn't have the F in there, that was from an old female, I'm sure, represents the average number of dates in a year for the brown-eyed participants. And then we have greater than or less than. So we can either hypothesize that the average number of blue has a greater number of dates than the average number of brown, or the average number of blue has a less than the average number of dates of the brown-eyed. And that is it for our beginning of t-tests, and I hope everybody has a great day. Thanks so much. Bye.